Hi, and thanks for joining me on this video about error analysis. And we're going to talk about the propagation of uncertainty in this video. We had been talking about the propagation of uncertainty with systematic errors. Now we're going to look at random errors, and specifically we're going to look at quadrature. In our previous video, we talked about Evel Knievel jumping over buses. Here's the bus again. And when we measure this bus, we came up with a length of about 45 feet, and we were uncertain to about a half a foot, plus or minus a half a foot. So it should be 45.0 here, 45.0 plus or minus a half a foot. That means, based on our uncertainty, that the bus could be as large as 45.5 feet and as small as 44.5 feet, because we have a half a foot of uncertainty. If we had two buses back to back, then the length of the buses, based on our measurement, 45 times 2 would be 90 feet. And the propagation of error, multiply the uncertainty, a half a foot, by 2, and that gives us 1 foot of uncertainty. So that means the two buses together, their measurement could be as large as 91 feet and as small as 89 feet. Now those are the worst possible errors. Those are the extreme possibilities. When you make your measurements, you're not going to be that far off. It's not going to be that bad. And this is a systematic error, meaning that the device that you're using to measure, whether it be tape measure, is consistently off by a foot or half a foot in either direction. Either you're measuring it too big or too small, a half a foot. More than likely, what's going to happen is that when you measure, you are not going to be measuring at the worst case scenario, but it's going to be slightly less. So when we look at these absolute errors, or systematic errors, they tend to overestimate our errors. But sometimes when you measure buses, and I've measured a few buses myself, the bus length might be a little bit bigger on one bus and a smaller on the other just because of interpolation. So instead of 45.5 or 44.5, you might be more than likely 45.1 foot on one bus and 44.9 feet on another bus. So the errors or uncertainties cancel each other out. They aren't always pushing it to the larger or smaller size. They cancel each other out. So that's why we use quadrature. Quadrature is used when the errors are random and independent, not systematic. And quadrature gives you the best estimate for the error. It gives you the most probable error and not the worst case. If you want to know the worst case, use just straight addition of the uncertainties. But here we're going to look at something a little bit different. We're going to look at what happens. We're going to look at what happens if your measurements are random and independent and the errors generated are random and independent. So let's say we have three values, x, y, and z, and we want to add those. We want to add x and y, we want to subtract z. So when we do that, we have to estimate our uncertainty, and if those measurements were made and the errors that you made in your measurements are random and independent, instead of adding up the uncertainties, you would square each uncertainty and then add it, and then take the square root, and that'll give you the more probable error. This is the example that we used last time. We looked at a polygon, and when we looked at systematic errors, we added each one of those uncertainties. We had a pretty sizable uncertainty. We had a perimeter of 298 inches around that polygon, and we added up the uncertainties, and that gave us 10 inches. If we use quadrature, that'll give us a more probable error. In this case, we take each uncertainty, square it, and then add it, and then take the square root of all of those added. So in this case, you would take 1 squared plus 2 squared plus 3 squared plus 4 squared, which gives you 30 inches squared. Take the square root, and that gives you 5.5. That's a lot less than 10 inches. So that's the more probable, based upon your random measurements, the random error that you have in your measurements. And notice it's about half of what your absolute uncertainty would be. Likewise, when you are multiplying and dividing numbers that have uncertainties, each one has uncertainty. In this case, you have x, y, and z. Multiply x times y and divide by z gives you q. The uncertainty in q would be the fractional uncertainties of each of those measurements, dx over x, dy over y, and dz over z. Square those, and then add those up, and then take the square root. Here's the example we had last time when we were talking about systematic errors. Remember that we took the fractional uncertainties last time, added them up, and we got a fractional uncertainty of 0.53%, or 5.53, which is about 53%. If we do it in quadrature, then we would take the fractional uncertainties of each measurement, 3 divided by 9, which is 0.33, 1 divided by 5, which is 0.2, and instead of just adding those, we're going to square them first, and then add them, and then take the square root. When we do that, instead of 0.53, we get a fractional uncertainty of 0.38. Once again, it's much less. So 0.53 is, for systematic errors, the worst case it could be, but the more probable, if your measurements are random, then, and your uncertainties are random, then that would be a 38% error instead of a 53% error. In summary, when you add up absolute or fractional uncertainties, depending upon the type of calculation that you're doing, you typically get the worst case scenario. You get the upper limit to your uncertainty. And this is common with systematic errors. But if your errors are random and independent, like interpolation errors or estimate errors, then you can use quadrature. Quadrature works for random and independent errors, and it'll give you a more probable error. So that's a little bit about systematic errors, estimating the uncertainty, and also estimating the uncertainty in random and independent errors.